All right, so we want the mass of KClO3 divided by the mass of the sample times 100%. And it's not going to be 100% KClO3 because this sample is going to be a mixture. You know, when I look at the unknown sample, this unknown sample is going to have an active ingredient. The active ingredient is going to be KClO3, and then it's going to have some inert ingredients. The inert ingredients are other stuff, like KCl or whatever else they decided to put in here. So the only thing that's going to decompose is the KClO3 in here. We can figure out how much KClO3 we generated by capturing the oxygen that comes off as a product. And so the mass of the KClO3 is going to come from this. We're going to be able to figure out the moles of oxygen if we know the pressure of the oxygen, the volume of the oxygen over R, and the temperature of the oxygen. The problem is did we collect pure oxygen? No, we collected what we call wet oxygen. Wet oxygen is saturated with humidity. And so how do we relate these things, which are for pure oxygen, versus this? Because when I look at the volume in this beaker, you know, the volume of the water I generated, and we have huge graduated cylinders next to the stockroom window, which we can use to measure this volume to the nearest milliliter. But this is the volume of wet hydrogen I just collected. And when I equalize the pressures, that pressure is the pressure of that entire mixture, right? Not necessarily the pressure of pure oxygen. And so the trick here is, in this particular experiment, we do things two ways. And so let's take a look at the two ways we do this. So we start off here with air that's trapped in the test tube. And so we have our sample here. And the sample is going to have air trapped in here. And there's a stopper. And this is going to go to our flask here. And we left a little air pocket at the top of the flask. We didn't fill the flask all the way with water, but there's a small air pocket here. And in this tube, we have this tube filled with air. And then most of this flask was filled with water. Like this. Okay, well, let's just figure out what we have. Okay, over here we have this empty beaker, but this whole tube, oops, it's not filled with air. This whole tube's filled with water. There are no air pockets here. It's an empty beaker, so if any water is pushed over there, that water had to come because gas was being generated over here. Now, is this dry air or wet air? Is this dry air or wet air that's trapped right now? This is before we started heating anything up. This is wet air. Why is this wet air? It's wet air because it's in contact with liquid water. Liquid water will evaporate, saturating this to 100% humidity. And so this is what we call wet air or humid air. It's actually going to be more humid than the lab air here. Okay, so what do we know? Do we know what the volume of the air is? This is the volume of the wet air. Do you have any idea what the volume of wet air is? No, we have no idea what the volume of wet air is. You know, it's whatever the volume of our test tube is, plus this hose, plus this little space above here. Do we need to know what the volume of wet air is? No, we don't need to know the volume of the wet air because we're going to look at this mixture as being an Avogadro's mixture. An Avogadro's mixture says, what about volumes? Avogadro's mixture says that the volumes are additive. We know what the pressure of this wet air is. What is the pressure of the wet air? The pressure of the wet air is the same as the barometric pressure. And so what is the barometric pressure? The barometric pressure we're going to measure. And what we're going to actually measure is not the corrected barometric pressure, but the uncorrected barometric pressure. And the barometer is sitting over there. So how do we measure barometric pressure using a barometer? And so let's talk about the barometer next. If you look at the barometer, there's going to be a long glass tube filled with mercury in here. And so our barometer is going to be like this. There's this glass tube, mercury in here. And on the side of the barometer, there's a metal knob. This metal knob, if you twist it, it adjusts a metal plate that's attached to the front of the barometer. And so here's the metal plate. And so rotating this knob will adjust the height of this plate. Actually, that will bring it up or down. What we want to do is we want to raise the plate or lower it so that it sits right on top of the meniscus here. And so this is our liquid mercury column. We want to lower the plate down so that it matches. And so let's show that here. Let's blow this part up. The plate's going to look like this. So we get the top of the plate to match the top of the meniscus, which is convex for mercury. And the first line on the plate is the zero line here. It's the zero line. And so this line, since it lines up with the meniscus, is what we want to read on the scale. And the scale is printed over here. So let's say this is say this is 750, 751, 752, 753, 754, 755. So when I look at where the meniscus lines up, it lines up between 754 and 755 millimeters of mercury. Right there. Since the precision of our barometer is to the nearest tenth of a millimeter, we should estimate that. It looks like it's 754 point what? A little more than halfway, so I'd say 754.6 maybe as a guess. And so you're allowed one estimated digit or one guesstimated digit according to the rules of sig figs, and you just estimated it along the scale here. But we don't have to do that because on this plate we have a vernier scale etched into it. In other words, this is a vernier caliper, and the vernier scale is going to have markings like this. It's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so we don't have to guesstimate this. We can get this 10th digit to high precision by using the vernier. Now, how do you use the vernier scale, which is etched into the plate itself? Well, the vernier scale, what you're doing is you're looking for a match, any match, it doesn't matter. And the match is between the left and the right side. And so if I look at line 1, it doesn't match with anything. Line 2 doesn't match. Line 3, line 4, line 5. Let's see. Actually, I need to do this to better scale. Do this. So this is 754, 755, 756, 757, 758. Okay, do you see the 758 line here matches with the 6 line here? Well, 758, that doesn't matter because we know the height of the mercury is 754 point something. So we don't care about the numbers on the right side. All we care about is the number on the left side. The number on the left side is 6. And the 6th line matches a line on the right side, whereas all the other lines are mismatched. And so what this tells us is it just tells us the 10th digit. And so since the 6th line you can follow all the way across like this, then that means the measurement here is 754.6 millimeters of mercury. And so this came from this. Okay, is that clear how to use it? All right, and so this is what we call the uncorrected barometric pressure. Why is it called the uncorrected barometric pressure? It's called the uncorrected barometric pressure. This is a good pre-lab question because, did it say in the lab? Because of the temperature of the barometer? Did it say? Sometimes when you're doing when you're reading through the lab, you have to do some external research. Not everything's going to be written in the lab notebook, and sometimes you'll have to look in other sources. And so why do we have to do a barometer correction?
The air is not at 0. The air is not at 0 degrees here.
Yeah, because the barometer was not calibrated at room temperature, or whatever temperature it is today. The barometer was calibrated at 0 degrees C. Now what happens with liquid mercury is, as the temperature warms up, the liquid mercury expands a little bit. And so the density changes with temperature because the volume increases. And so what we have to do is we have to correct for the expansion of mercury. Well, it's not so big. You know, if you have a column a meter high, the expansion is only going to be 2 or 3 millimeters. Right? But still, 2 or 3 millimeters leads to an error that we should correct for, systematic error. And so pre-lab questions would be like, why is a barometer correction necessary? And what two factors influence the degree of expansion of the mercury? You know, temperature, the material is mercury. So what two things affect the degree of expansion of mercury? Temperature is one, and pressure. The atmospheric pressure. This is why did you guys look at the table? When you look at the table, what's the magnitude of corrections we're applying? What do they range from? From what to what? Over what temperature range do you have in that table? Over what pressure range do you have in that table? So you can get an idea about that. And so let's take a look at the correction. So let's say the temperature of the barometer. The barometer itself has a thermometer mounted on the surface of it, so we can figure out, what the temperature of the barometer is itself. And it could be a little different than the temperature of the air in this room. But let's say the temperature of the barometer was 24.3 degrees C. 24.3 degrees. So these are just numbers that are made up. So how would I apply the correction? Well, the correction is going to depend on two things. It's going to depend on the temperature and the pressure. And so the pressure range is between, it's 754.6. And so we're okay going from 740 to 760 here. And so at 24 degrees C, what is the correction that we need to apply? At 24, read it off the table. At 24 degrees C, what is the correction that needs to be applied? 2.9. And so what that means is at 24 degrees C and 740 millimeters of external atmospheric pressure, you know, the more pressure you have, at 24 degrees C and 740 is expanded by 2.9 millimeters. Although this is backwards from what I'm thinking. At 760, what is it? 3.0. So not much difference. At 26 degrees, what is it here? 3.1 and 3.2. Okay. Unfortunately, we don't have, you know, these temperatures and we don't have that pressure, but what we're going to do is we're going to do a linear interpolation. Have you done interpolations before? Probably not. People who used to do logarithms by tables were pretty good at interpolations, but nowadays not so much. All right, the first interpolation we're going to do is we want the temperature not 24, not 26. We want the temperature at 24.3 degrees C, right? And we've got to figure out what is the correction here. You know, it's not 2.9, it's not 3.1, it's somewhere between. And so what we're going to do is we're going to do linear interpolation by this, by setting up some ratios. And so 24 to 24.3 is 0.3 degrees of the way over total distance from 24 to 26, that's 2 degrees C. And so I'm going to just omit units to keep it simpler here. And so the first ratio is 0.3 out of 2. So 0.3 out of 2 is going to be the same as x out of, well, what's the total distance here? So from 2.9 to 3.1, coincidentally, it comes out to 0.2. And so this is going to equal x over 0.2. Therefore, x is equal to 0.03. And so what we are is we're 0.03 out of 0.2 down. So the correction here is going to be 2.93. Does everybody see that? And so we do the same thing over here. 0.3 out of 2 is the same thing as x over 0.2. Well, it's the same distance. The total distance is 0.2. We're looking for what fraction of this distance we traveled. We just calculated it. It's 0.03. And so the correction here is going to be 3.03. Okay. And so we have at 740 and 24.3 degrees C, we have 2.93. At 760 at 24.3, we have 3.03. But we're not at 740, we're not at 760. Where are we at? We're at 754.6. And so we're somewhere over here, 754.6. And so we're going to do the same thing. We're going to set up some ratios here. And so this is how far. So 40 to 54.6 would be 14.6 parts out of 20. And so we'll have 14.6 out of 20 is one fraction. And then the other fraction is this total distance here in x. So we want x to be in the same ratio. So x over, now this is going from 2.93 to 3.03, so the total distance is 0.10. And so this is going to be equal to x over 0.10. So that means x is equal to what? So 0.1 is 1.46 divided by 20. What's 1.46 divided by 20? 0.073. Is that right? Okay, 0.073. And so we're 0.073 past 2.93. And so that would be 2.93 plus 0.073 is going to give me 3. Let me do this in a different color. It's going to give me 3.003. That's a correction there for the expansion. Does that make sense? So what we're going to do is we're going to take our uncorrected barometer reading and correct it now. So the uncorrected barometer reading was 754.6 millimeters mercury, uncorrected. And then the correction here is 3.003 millimeters of mercury. We subtract that, we're going to get, actually this 3 is not that. We're going to get 751.6, rounding it to the correct number, sig fig. Is that okay? And so this would be our corrected barometer reading. All right, the next thing that happens is we generate the air, actually oxygen mixture. Let me do that here. So we apply heat. The KClO3 starts to decompose and air is generated. So we have the air that's still, not air, actually oxygen's generated. I'm gonna color oxygen red. So we're going to generate some O2. This O2 is going to be pushed into the flask here. And push the water out of the flask. We still have air that's trapped in here, and we still have water vapor that's trapped in here because this is all over water. So there's water. So this is a mixture of 3 gases. Well, more than 3 gases because air itself is a mixture. So we have this. Hopefully no air got trapped in our line here, so our line's filled with liquid water. This liquid water is going to spill out into the beaker over here. And fill up the beaker. All right. So what do I know about this right now? 1, is the pressure of the gas inside here the same as atmospheric pressure? Is it the same as atmospheric pressure? No. No, it's actually less than atmospheric pressure because if you treat this as a seesaw, here, the right side is heavier, right, than the left side, meaning the atmosphere is pushing down with more force. And so the pressure in here is less than the atmospheric. Well, how can I get the pressure to be the same as atmospheric? What I need to do is I need to lift up the beaker to back siphon water in here and compress the gas a little bit to get the pressure up. And so what I'm going to do is I'm going to raise the beaker until the liquid levels match. When the liquid levels match, then the pressure pushing down here is the same as the pressure pushing here because the seesaw is now horizontal. It's balanced. Does that make sense? Okay, then what I have to do is this. This is the volume of gas I just formed at atmospheric pressure or barometric pressure. And so what I need to do is I need to pinch the hose here. Right? I did this already in the demo. I need to pinch this hose here and then remove it. And so I have this beaker full of water now. And so I got the volume of H2O liquid. And so we got to keep track of things now here, because I had originally I had some volume of wet air, and then what did I add to this wet air? I added a certain volume of wet oxygen. The volume of wet oxygen, well, this is Avogadro's law. So the volume of wet air plus the volume of wet oxygen gives me volume total. Avogadro's is for constant pressure. So the pressure of the air, wet air, is equal to the pressure of the wet oxygen, which is equal to the barometric pressure. So that gives me V total. The volume of wet oxygen I just generated is this. The volume of H2O liquid will be equal to the volume of wet oxygen. What's the pressure? The pressure of this mixture is equal to the barometric pressure. Okay, so now I have all this, and I got to figure out these things. I don't want the volume of wet oxygen. I want the volume of dry oxygen. I don't want the pressure of the mixture. I want the pressure of dry O2. And I want the temperature of dry O2. And so how am I going to get these? What is the volume of dry O2? Here. Well, the volume of dry O2, according to Avogadro's, is the volume of wet O2 minus the volume of water vapor. And so if I take the wet O2 and subtract out the water vapor, then I have the volume of dry O2. But do I know the volume of water vapor in there? No, I don't. I don't know the volume of water vapor, but something that's much easier than doing the volume of water vapor is to get the pressure of the water vapor. That I do know, because the pressure of the water vapor is going to depend on the temperature. And so what I want to do is I want to switch. So far I've been dealing with Avogadro's because we're just adding up the volumes, right? Displacing volume. And so what I'm going to do now is I'm going to switch from Avogadro's to Dalton's. When I switch over to Dalton's, then what's happening here? Dalton says what? Well, over here, Avogadro's is going to say the volume of wet O2 is equal to the volume of the H2O gas plus the volume of the dry O2. Is this going to be easy to get? Well, we don't have the volume of H2O gas, do we? But if I switch to Dalton's, then what can I say? Yeah. Well, what I can say is this. Over here, the pressures are all the same. And so with Dalton's, we could say that the volume of wet O2 is equal to what? Yeah, is equal to the volume of dry O2. And so the wet O2 volume and the dry O2 volume are the same thing. Over here, what was the pressure of the wet O2? The pressure of the wet O2 was equal to the barometric pressure. You know, all the pressures are the same because this is Avogadro's. And we equalized out the pressures. But over here, when we think in terms of Dalton's, then this is what I have. The pressure of the wet O2 is no longer equal to the barometric pressure. Or is it? No, it is. It's still equal. The pressure of the wet O2 is equal to the barometric pressure. Over here in Avogadro's, the pressure of the wet O2 is equal to the barometric pressure, which is equal to the pressure of the dry O2. Right? But over here, is this equal to the pressure of dry O2? No, here it's not equal. And so what we have here is this. The barometric pressure, which is the total pressure, is going to equal the pressure of the dry O2 plus the pressure of the water vapor. And therefore, if we want the pressure of the dry O2, the pressure of the dry O2 is equal to the barometric pressure minus the vapor pressure of water. And so here we have it. But we had to do a switch over to Dalton's to figure it out easily. All right, this is one way we're going to get it. The other way we're going to get it is by doing this. I'll show you in just a sec. So we calculate the moles of O2 by the pressure of the pure O2, the volume of the pure O2, or the temperature of the O2. The temperature of the O2 is going to be the same as the temperature of the wet O2. Everything's in thermal equilibrium. And then from the moles of O2, we can go using the balanced chemical equation to the moles of KClO3 that must have decomposed. And from moles of KClO3, we can go to grams of KClO3. And then we can plug that in. This is calculation 2. Calculation 1, we're going to do an alternate calc. Calculation 1 is we're going to figure out from grams of O2. The grams of O2, this is going to come from the initial mass minus the final mass of the mixture. And the difference is the grams of O2. Grams of O2 to moles of O2, moles of O2 to moles of KClO3, moles of KClO3 to grams of KClO3. And then we're going to compare the two calculations and see. Yeah. The percent KClO3 by mass should come out the same in both calculations. All right, any questions regarding this? No. All right, I'm going to stop the discussion here. This is a pretty short